Today in this video, I will be talking about the concept of the limit of a function. The concept of limit marks the beginning of the calculus. So, this is the first video in the series of differentiation. Hope you will like the entire differentiation series. Let's consider a function f of x equal to x square minus 1 upon x minus 1. Obviously, when we calculate f of 1, it is 0 by 0, which is meaningless. So, the function is not defined at x equal to 1. But look at the function on this Desmos graphing software. When I approach the function from left or when I approach the function from the right, an amazing phenomena is taking place. The value of the function is getting closer and closer to 2. You can see it clearly with x equal to 0.9 to 0.99 to 0.999 and so on. X is approaching to 1 and the value of the function is approaching to 2. Similarly, from the right also, the function is approaching to 2. Let us see one more example. Here also, the value of the function at x equal to 1 is 0 by 0, which is meaningless. But when we approach x equal to 1 from the left, starting from x equal to 0.9 to 0.99 and so on, the value of the function is approaching to 3. Similarly, from right side also, when we approach starting with x equal to 1.3, 1.2, 1.1 and so on, and x is approaching to 1, the value of the function approaches to 3. So as in case of this function, we have seen when x is approaching 1 from left, f of x is tending to 3. This is called left hand limit and we write it as limit x tends to 1 minus or x tends to 1 minus. Similarly, when x is approaching x equal to 1 from the right, f of x is again tending to 3. This is called right hand limit and we write it as limit x tends to 1 plus or x tends to 1 plus, this way. Hence it is likely that left hand limit and right hand limit will be equal. So for the existence of this limit x tends to a f of x, it is essential that limit x tends to a minus f of x and limit x tends to a plus f of x should both exist separately and they must be equal. Well, when we try to solve the questions based on limits, we usually use different techniques to solve it, and based on these techniques we can call them as direct substitution method or factorization method or formula method. So let's take a question. Evaluate the limit of x plus 3 when x is tending to 3. So here I can directly substitute the value of x as 3. So if I say applying limit, so I can directly substitute it as 3 plus 3 and I'm getting the answer as 6. Now the meaning is at a point of the domain x equal to 3, the limiting value of this function is 6. Now the meaning is when we are approaching x equal to 3 from the left or when we are approaching x tending to 3 from the right, the maximum value that this function can achieve in the neighborhood of x equal to 3 is 6. Now let's take another question. We have to evaluate the limit of this function. Now it's a function x4 minus 81 upon 2x square minus 5x minus 3. Let's apply the direct substitution method, which means if I am going to substitute x as 3, interestingly my answer would be 0 by 0, which is obviously meaningless. Now, so this means the direct substitution method is not working here. I will have to apply factorization method. Once we cancel the common terms, now the expression looks like this. And in this one, if I apply the limit or the direct substitution method, it becomes 108 upon 7. So I can say that for this function on the number line, or say in the domain of this function at x equal to 3, when we were approaching this function either from the left side or from the right side, the maximum value that this function could attain over there was 108 upon 7. That's why this is the limiting value of this function, or we call it as limit of the function. Let's take another question. Evaluate the limit of the function sine ax upon sine bx when x is tending to 0. Again, here if I apply the direct substitution method, this becomes 0 by 0, which is meaningless. And we cannot factorize it. So let's try the third method, which is the formula method. So here I am dividing the numerator and denominator by x. And then I'm dividing and multiplying the numerator by a and dividing and multiplying the denominator by b. When x is tending to 0, ax and bx both will tend to 0. And a and b, these two numbers a and b, they are constant. They can be taken out. So a by b is completely out. And I'm writing my limits now as limit ax tends to 0 sine ax upon ax. Similarly, limit bx tends to 0 sine bx upon bx. Now, if I apply the formula of limit x tends to 0 sine x upon x is equal to 1, which means when the function sine x upon x, when x approaches to 0, the limiting value of this function is 1. So utilizing the same fact over here, it is a upon b times 1 by 1. That's how the limiting value of this function is a by b. Let's take another question. Evaluate the limit cos 2x minus 1 upon cos x minus 1 when x is tending to 0. Now from trigonometry we know that cos 2x is equal to 2 cos square x minus 1. So if I substitute this value back here in the question, it becomes 2 cos square x minus 1 divided by cos x minus 1. Now if we take 2 common, it becomes 2 cos square x minus 1 upon cos x minus 1. And in cos square x minus 1, we can apply the formula a square minus b square, which is a plus b, a minus b. So if we apply this formula, we get cos x minus 1 times cos x plus 1 upon cos x minus 1. And we can see these two are common factors. If we cancel this and we take this 2 out as a constant, now we are left with limit x tends to 0 cos of x plus 1. Now if I do the direct substitution method, means if I apply the limit now, it gives me 2 times cos of 0. Cos of 0 is 1 plus 1. So overall the answer is 2. This means when x is tending to 0, the limiting value of this function is 4. The question, evaluate the limit tan 2x upon x minus pi by 2 when x is tending to pi by 2. To solve such questions when x is tending to a, it's always better to substitute something similar, like in this case h is equal to x minus pi by 2, such that x will become pi by 2 plus h. And now obviously when x is tending to pi by 2, h is tending to 0. So I have the question limit h tends to 0 tan 2 times pi by 2 plus h, because this is the substituted value of x, divided by x minus pi by 2 will become h. Now after simplification we are getting limit h tending to 0 tan 2h upon h. This is because tan pi plus theta is always theta. That's how tan pi plus 2h is tan 2h now. Now this, as for the formula, if you go back and remember that formula, it was limit h tends to 0 tan h upon h will be 1. So in my case the angle is 2h. Now to make this also 2, I am multiplying the denominator by 2 and I am also dividing my denominator by 2. So if you simplify, this 2 goes to the denominator and it becomes 2 times limit h tending to 0 tan 2h divided by 2h. And we can have the same logic here also, that when h is tending to 0, obviously 2h will also tend to 0. So this limit can be converted as limit 2h tends to 0 tan 2h upon 2h. Now if I apply the direct substitution method, this much gives me 1. So it is 2 times 1. That's how the limiting value of this function is 2. Examine this limit now when x is tending to 2 f of x, and this fx is defined as x square plus 1 when x is less than equal to 2 and x plus 3 when x is greater than 2. Now since here we have to examine the limit, so we will try to find the left hand limit as well as the right hand limit, and we know if these two limits will be equal, then this limit exists and the common value of these two limits will become the limiting value of this function. To find the left hand limit, we write it like this: limit x tends to 2 minus f of x, which is limit x tends to 2 minus. Now when this function is below 2, the value of this function is x square plus 1. So let's make it clear with a number line also. If this is the given function, this is the number line, and this is the point x equal to 2 where we have to examine the limit. If you look at the definition of the function, it says when x is less than equal to 2, the value of the function is given by f of x is given by x square plus 1. And at the same time, when this function is greater than 2, now the value of the function is given by f of x now is x plus 3. So accordingly we can see the function is behaving differently. Let x equal to 2 minus h, such that when x tends to 2, h tends to 0. So limit h tends to 0, 2 minus h whole square plus 1, limit h tends to 0, it is 4 plus h square minus 4h plus 1. It is limit h tending to 0, 5 plus h square minus 4h. Now if I apply the direct substitution method, or if I say I am applying the limit, I will get 5 plus 0 minus 0. So the value of the left hand limit is 5, which means when x is approaching 2 from the left side, the answer is 5. Now let's talk about the right hand limit. We can see from the number line when x is greater than 2, the function is given by x plus 3. So to calculate the right hand limit, I will write it like this. And then we say let x equal to 2 plus h, such that when x is tending to 2, obviously h is tending to 0. So now I can write limit h tends to 0, 2 plus h plus 3. So basically it is limit h tends to 0, 5 plus h. Again, if I use the direct substitution method, or say I am applying the limit, it gives me 5 plus 0, which is 5. So we have seen the left hand limit and the right hand limit both are equal here and both are equal to 5. So this common value 5 becomes the limiting value of this function, and hence the limit exists and the value is 5. Well, if you could understand what I was trying to explain, please like and subscribe to my channel. And if you want to be notified for my next video, please press the bell icon also. Thank you.